In this standard transformer architecture, input tokens pass up a growing stack of dense layers. Historically, scaling means adding layers for spatial depth. As the stack grows, the parameter counter crosses the 1 trillion threshold because each new layer adds billions of unique weights. This spatial scaling demands massive clusters of GPUs just to hold the model in memory, creating severe hardware bottlenecks before inference even begins. Relying exclusively on massive parameter expansion is reaching physical limits. Static architectural size is no longer a sustainable vector for improving artificial intelligence logic. An alternative structural design is the Recurrent Depth Transformer, or RDT. Instead of relying on spatial depth, which means stacking static, single-use layers, an RDT leverages temporal depth, reusing the same set of layers over time. This diagram shows the towering stack of transformer layers conceptually collapsing down into a single compact structural block. During inference, data routes iteratively back through this exact same block, rather than passing through unique subsequent layers. This architectural loop decouples a model's complex reasoning capacity from its baseline parameter count. By shifting compute away from training size and moving it directly into the inference phase, temporal depth alters the scaling laws of frontier models. The core execution engine of this architecture is the recurrent block, which continuously loops the hidden state up to 16 times per pass. But looping introduces a critical stability risk. A highly uniform stream can suddenly become turbulent and expand chaotically into unpredictable ripples. In a neural network, if you keep looping the calculation, hidden state values can easily explode or drift into statistical noise. To prevent drift, the model uses linear time invariant injection. The update rule combines the previous state, original input signal, and current computation. Learned matrices blend these at every step, with the original input acting as a stable anchor to align the output across iterations. Without this continuous reinjection of the original input signal, the model would lose context and drift away from the prompt it was supposed to process. Controlled state injection transforms what would be a chaotic mathematical loop into a stable, prolonged reasoning engine. The primary engineering critique of RDTs is compute efficiency. Repeating the identical mathematical computation 16 times wastes processing power. Inside the recurrent block, the network expands into a 384-node mixture of experts array. Dynamic routing activates different experts each loop. Iteration 1 routes through nodes A, B, and C. In iteration 2, the token routes through entirely different nodes, X, Y, and Z. Because different experts activate on each pass, the network avoids repeating prior calculations entirely. Instead, it extracts novel features with every cycle. Temporal depth combined with sparse routing creates a system capable of extracting dense insights without expanding its base parameter footprint. There is also the opposite problem, overthinking. Forcing too many iterations on simple queries causes the model to drift past the correct answer and hallucinate. This visualizes adaptive computation time. Look at these two tokens, one complex, one simple, each with a compute budget gauge. The simple token loops 3 times, empties its gauge, and exits early. The complex token loops 15 times until its gauge empties. By cutting processing short on easy parts of a prompt, adaptive computation time optimizes total compute efficiency and prevents wasted cycles on trivial syntax. Giving the model the mathematical ability to know when to stop processing solves the core efficiency problem of recurrent loops. Even with efficient compute routing, high iteration inference introduces a secondary bottleneck, massive key-value cache memory overhead. To manage this specific memory load, the architecture uses multi-latent attention. This diagram shows a massive array of key-value data blocks shrinking down into a single compressed, low-rank representation block. This process achieves a 10 to 20 times reduction in memory usage. This aggressive compression makes high-iteration RDT models viable for deployment on standard commercial hardware. Solving the key-value memory bottleneck is the final architectural step that allows temporal depth models to challenge trillion-parameter systems. We can see the empirical benchmark evidence in this data table, directly comparing a 770 million parameter RDT to a 1.3 billion parameter standard transformer. The performance bars for both models extend to identical endpoints. The recurrent model achieves matching systematic generalization despite utilizing nearly half the parameters. This equivalence explicitly challenges the industry assumption that baseline reasoning requires massive parameter expansion. Raw knowledge capacity is no longer the sole metric for determining a model's operational utility. To understand the ultimate advantage of an RDT, we have to contrast its internal mechanics against the current industry standard of chain-of-thought prompting. Chain-of-thought forces the model into narrow, sequential logic, generating a rigid, one-directional chain of text. Watch it fade away. In its place, a continuous, multi-dimensional point cloud expands. This is latent space reasoning. Logic and exploration occur entirely inside hidden state vectors. Operating in this continuous space acts like a breadth-first search, testing multiple complex logical pathways simultaneously within a single forward pass. The core bottleneck in frontier models is not knowledge retrieval, but combinatorial reasoning. Shifting compute to dynamic latent space loops proves that the next evolution in AI architecture lies in deeper, hidden computation.